Thank you. All right. It is really quite an honor and a pleasure to be here. I don't get to work on Kuiper Belt objects as much as I'd like to. I often end up working on exoplanets. That pays the bills. But the techniques are very similar. To learn about the interiors and evolution of exoplanets, we often have to resort to weird tricks, like looking at uh, planets that are very close to their stars and figuring out their minimum core mass fraction, or else they'd be tidally disrupted, or watching as planets spill their guts onto the surface of a white dwarf or disintegrate, and doing transmission spectroscopy. So in the same vein, I'm going to be talking about how we can assess the interior structure and evolution of Kuiper Belt objects using weird tricks, a little clickbait title. Okay, so questions that I have when I think about interior structure and evolution include things like, when did the Kuiper Belt objects accrete and form, and when did they heat up and differentiate? It could be like asteroids. They accreted quite a lot of aluminum-26 and they melted almost immediately within less than 1 million years or so. Or possibly they took longer to accrete. Aluminum-26 had decayed. Maybe they took many tens of millions of years. Another question I've often wondered is how partial or complete was the differentiation? Because there are different theories about this. If small KBOs might not have differentiated at all, and I'll talk about the Pearson and Nimmo result, but on the other hand, I think that Sharon-sized bodies should differentiate, but maybe not completely. Maybe they retain some undifferentiated rock ice crusts. And then another question that we're faced a lot with is how do they outgas? How do they put volatiles on their surfaces? Do they extrude cryolavas? Do they outgas volatiles like N2? And how much do they do? I may be exaggerating when I say tens of kilometers of N2 ice, but there is some evidence from glacial features, that there were many kilometers of N2 ice on the surface of Pluto in the past. But on the other hand, we've heard that the loss of N2 is considered to be minimal, and that would exclude that sort of possibility. So questions about that. And when did all these dynamical instabilities in the solar system occur? The Kuiper Belt is a probe of Neptune's migration outward associated with the dynamical instability of the outer planets. And there's a question about when this occurred. It could have occurred immediately after the gas in the disk dispersed, maybe less than 10 million years. On the other hand, it could be when planetesimals were able to initiate through their, the scattering of planetesimals, a dynamical instability around 30 to 60 million years. And so we'd like to assess that. So these are the sorts of questions I have, and trying to look at different objects to try to assess that. So let's start with the smallest bodies and ask whether they differentiated at all or not. And there's this plot, this paper by Pearson and Nimmo, which is really great. It looks at the mass and radius of Kuiper Belt objects for which we have reasonably precise data, and then infers a bulk density as a function of their radius. And so we've seen this plot before, that small bodies less than 300 kilometers do not seem to be very dense. Their densities sort of cluster around 0.5 or 1 gram per cubic centimeter, whereas larger bodies, I think this is Eris, Pluto, they tend to have higher densities. And these densities are consistent with a rock fraction of about 70%, let's say. And as they get very dense, they tend to collapse porosity. And if they're not dense, they retain significant porosity. So that was the interpretation. And so the question is, what conditions would lead you to have porosity or not have porosity? Pearson and Nimmo considered porosity to collapse if ice became even a little bit able to flow, which didn't even require it to melt, but certainly if it melted, you would collapse porosity in their conception. And if it even approached 273 Kelvin, it would collapse. So that requires that they had to stay cold in order to retain porosity. So in this plot from that paper, they plot the final densities of different objects with these radii and rock fractions. as a function of their time of formation, which is really a statement of how much aluminum-26 they contained at the time of their accretion. So for example, a body with 70% rock and a 300-kilometer radius, this dashed yellow line, they would be dense and they would have collapsed porosity if they formed in the first 4 million years. And if they took 5 or longer millions of years to form, then they would have so little aluminum-26 they wouldn't heat, and they would retain porosity and be low density. So they inferred that it took longer than 4 or 5 million years for those objects to form. In a separate thing I do, I try to ask the question of whether CI chondrites could be samples of KBOs. CI chondrites have clear evidence of aqueous alteration. They definitely had liquid water that reacted with the minerals. And if it's the case that KBOs could not have differentiated and they could not have had water at all, then they could not be the parent bodies of CI chondrites. But there is different modeling that was done by my collaborator, Mark Neveu, on 87 Sylvia, which is a P-type asteroid in the outer asteroid belt. And it has 2 moons, Romulus and Remus. And it's pretty small, mean radius of about 135 kilometers, but it is oblate. And therefore, these satellites' orbits potentially could precess. The main point of the paper by Carey et al. Was to investigate the astrometry of the moons and derive a J2. And they basically could not resolve a J2 from 0. And their interpretation is that the mass in this body was very centrally condensed. But it's a very small body, so it's hard to imagine how you would escape a uniform density. And the model they came up with is that you did have, and I should use, this is the icy dwarf code that I'll talk about a little bit later, that Mark used to calculate the internal temperatures, thermal evolution, flow of water, et cetera. What they inferred is that you retain porosity throughout most of the body, but you do melt ice, and the water was able to percolate down through the porous rock and form a filled-in icy core that has high density because it's filling all the pore space overlaid by porous layers. And this is a way of getting the concentration high and reducing the J2 moment. And they modeled this as consistent with formation at about 6 million years or later, so that there was no live aluminum-26, but it probably could withstand a little bit of aluminum-26 and yield the same result. But it's definitely a different way of looking at these things. It's not necessarily the case that when you melt ice that you collapse porosity. So we are beginning to understand that small bodies could have some melting of ice and have some sort of differentiation, although this is not the way we usually think of differentiation, but you are putting material in the core. So that's the small end. And what about the medium size end? So objects the size of Sharon, and this is how I got my start modeling Kuiper Belt objects, created a thermal evolution code in 2009 that allowed for radiogenic heating and differentiation of rock and ice, but only when the temperature was high enough to allow rock to flow through the ice. And one of the main findings of my work is that bodies the size of Sharon could definitely have liquid inside of them. And this is a plot of the mass of liquid in the body versus time, billions of years. And potentially, in one model at least, it was able to survive to the present day. But you'd have a rocky core and a liquid or icy water mantle, but it's always in those models overlaid by an undifferentiated crust of rock and ice that was many tens of kilometers thick, sometimes 70 kilometers thick. And that's simply that if you start with a homogeneous body, if you start with a cold start, it's just never warm enough to allow rock and ice to separate, even through density inversions, really Taylor instabilities. You just cannot get that separation of rock and ice. And so this is a really kind of a robust prediction, is if you start by accreting small bodies, and if they never get really hot, you really should have rock ice, undifferentiated primordial sort of crusts on their surfaces, and it's really hard to get rid of that. Now, Mark was my PhD student, and he took that thermal evolution code and really souped it up by adding a lot of effects, including geochemistry and core cracking, thinking about geophysics of the core under certain conditions, especially as the temperatures change in the core. Minerals can crack, that can admit more porosity, more flow of liquid. You could also have serpentinization reactions that close the pore space. And there's a lot of feedbacks in there. The code is publicly available. It's not the easiest code to use, but it's got all of these physical effects in there. And so we modeled a number of bodies, including Ceres and Sharon, back when we did this work 10 years ago. This is a plot of the temperatures inside a Ceres type body as a function of distance from the center. And you're looking at time on a logarithmic axis. And these colors denote different temperatures with water melting at these sort of orange temperatures. And this one, it's a model with a large core, and this is a model with a small core. Very interesting feedbacks can happen when you start to look into this. It could be the case that the thermal conductivity in the outer layers is low, and it doesn't admit the transmission of heat from radiogenic heating, and then the temperatures build up, and then it can melt those shells, and then it makes the rock ice layers thinner, and those are the ones that have the high thermal conductivity. So it's like melting the blanket, and then the heat can get out, and then it can freeze the oceans, and then it can repeat this process. The heat is sort of throttled as it's getting out. So you can have these transient and intermittent oceans. Many weird behaviors are possible. And this is one type of model for Ceres. And then this was our models for Sharon. And we also varied things like what is the fraction of the icy layers mass that is actually like silicate fines that can't separate until it melts. And so that's a low value and that's a high value. And we get all of these different behaviors. And I think it's fair to say that it's pretty complicated depending on what assumptions you make. But in general, if Sharon accreted in less than 4 million years, it would have enough aluminum-26 that the ice shell would, the crust would totally melt. And then you would have ice on the surface. Anybody in this size range should have ice on the surface if they routinely accreted before 4 million years. And if they accreted after 7 million years, then there's no way that would happen. They should have these rock ice crusts. And since most Kuiper belt objects don't appear to have pure ice surfaces, we sort of infer that KBOs generally form pretty late with low aluminum-26, but where in that 4 to 7 million year range they formed is still maybe an open question. All right, so we found it really useful to look at one specific example of Haumea as a weird medium-sized KBO with a very unique history that allows us to make progress on these questions. Haumea is my favorite dwarf planet. Haumea is my third favorite dwarf planet. We've heard a lot about it, and it's a really unique object with a pure water ice surface. Possibly there's a mixture of clay-like minerals, kaolinite in there, unclear. Has 2 moons, Hi'iaka and Namaka. And from that, we can derive a mass. More recently, it's been discovered it has a ring. And it's also a very fast rotating object, 3.9 hour rotation period. And it has this dynamical family. I will not call it a collisional family. There's a dynamical family of objects that are also pure water ice that orbit the sun in the same manner as Haumea and clearly are associated with it. And they're dynamically associated with it, and they have water ice compositions like Haumea. They're almost pure water ice. This question about whether it's crystalline or amorphous and what that means for the age of the surface, I just want to point out that Simon Porter and I, back in when he was my grad student, calculated the effect of micrometeorite impacts on the heating of ice, and just micrometeorite impacts can anneal the ice. So cosmic radiation turns it from crystalline to amorphous, but micrometeorites can turn it back from amorphous to crystalline. So I'm not sure we can use that as an estimate of the age of the surface. But anyway, these objects also have pure water ice surfaces, so they're associated with Haumea. They comprise only 3% of Haumea's mass, which is an interesting number. They also have velocity differences compared to Haumea that are only a few hundred, like 150 meters per second variations, and that's interesting. And of course, all of them orbit in the same orbit as Haumea, which is in a scattered disk object. Its inclination is like 28 degrees, and semi-major axis 43 AU. So it's really far out there. And yeah, the occultation shows it has a ring and all very interesting stuff. So when it was discovered, it was hypothesized to have had this dynamical family because of a collision. The collision would give it a high angular momentum state and knock off fragments. And that made some sense, but there are problems with that hypothesis, including the fact that you really expect a lot more mass than we've eventually discovered. You expect way more than 6% actually. You expect the family members to have velocity dispersions from the mean of the dynamical family that exceed the escape velocity of something like 800 meters per second, yet they all pretty much are under 150 meters per second. Ben has also worked on this question of whether the directionality of the velocity changes they received is consistent with ejection, and the sort of graze and merge collision that might produce this is not really consistent with their distribution of orbital elements. And then one of the main problems is that the probability of a collision like this in the current scattered disk, Hal Levison showed, is extremely low, 10 to the minus 3 or less. So there's problems with that. And working on these problems, my postdoc at the time, Jessica Noviello, was here, and I worked on a history for Haumea that we think satisfies all of these questions that I'll describe now. So, oh, that's interesting. I didn't know that figure could do that. Okay. All right. So the idea behind the model is that, first of all, there was a collision that gave Haumea a very high angular momentum, but it happened while it was a cold classical belt body. And so a collisional family would have been generated at that time, but it has since been scrambled by Neptune's migration. And I think that we can make analogies to Pluto. I remember reading once Alan Stern predicted Pluto should have had a collisional family if there was a Pluto and Charon impact. Where's all this other ejecta? And we've never really seen a collisional family. But of course, Pluto has had its orbit scrambled, and so would all the fragments. So a collision happened. It gave it very high angular momentum. And as high as that angular momentum was and how fast it was spinning, it started to spin even faster as its core formed. So as the rock separated from the ice and fell into the center of the body and formed a rocky core, if you've ever seen any science show, you know that the analogy is as an ice skater pulls in her arms and she'll spin faster. So for the same angular momentum, the angular velocity increased until the spin was so fast that actually it was able to fling material off. So it assumed a triaxial ellipsoid shape because if you increase the angular momentum to an object, you will take a sphere and you will turn it into an oblate spheroid. But if you add even more angular momentum to it, it will turn into a triaxial ellipsoid modeled, if it's uniform in density, as a Jacobi ellipsoid. And so in step 3, it was probably like that. And then at step 4, as it spins even faster, angular momentum is conserved, but the angular velocity is increased. And at the very tips of the long axis, the gravity actually goes to 0. And so you can get material that is just lifted off the body and goes into orbit around the body with almost no energy required. And so you form a ring of material orbiting very close to Haumea, and that can eventually do what you see in the last slide, where you have moonlets form in this ring of material. And the ring can actually viscously spread as a result. You could eject due to scattering. We don't model this part, but you could definitely eject moonlets as they scatter off of each other. We speculate that the velocity dispersions would be very low and comparable to the 150 meters per second, depending on how the orbits process and over time. This would take a very long time, so it may be more consistent with some of the directionality of the orbital elements that the family members need. But we think this is the origin. You have icy material lifting off of the surface, forming a ring, forming moonlets, and that forms the rings, Hi'iaka, Namaka, and the dynamical family members. Meanwhile, in Haumea, eventually, not only does it heat up inside to the point where rock separates, but you actually, at some point, crack the rock and allow hydration of the rock. And so you form, out of the dense olivine sort of core, you form a phyllosilicate core with density of maybe 2.6. And then that core, therefore, has swollen up, and that increases the moment of inertia, and for the same angular momentum, it slows down. So we aim to test this hypothesis in the 2022 paper. And we did this using two codes. One is the icy dwarf code that Mark wrote to model the thermal evolution of an admittedly spherical body. And the other is this Kyushu code that I wrote that calculates the hydrostatic equilibrium structure and shape of a differentiated, rapidly rotating body and calculates the triaxial ellipsoid shape that gives you equilibrium. And so we were looking for solutions that were like Haumea today, but had 3% more mass to account for the dynamical family members. And when you think about the angular momentum that those objects have as they leave the tips of the triaxial ellipsoid in Haumea, you need to have 13% more angular momentum. So we're wondering if there are states with that much angular momentum and mass, we could start with that much angular momentum and mass, evolve to a point, then remove 3% of the mass and 13% angular momentum and evolve to the present day point, and yet have the core be continuous across that. And I won't describe the whole parameter study that we did, but we think this is a reasonable solution that we have right after the impact. This was the mass of Haumea in present day units, and its angular momentum, and the spin period, 4.65 hours. After the core formed, and just as it was about to fling material, its period got down to 3.5 hours, and then these two have more or less mass ejected, and then after the core swells up, it slows down to the 3.92, and the core attributes are sort of continuous across that. So all of this says that to us that this is a consistent solution and a likely history for Haumea. And the nice thing about it is that we can make this timeline of events then. When do these things have to happen in order to match some of these observational constraints? So we presume that CAIs formed 4, 5, 6, 8 million years ago. Most of the KVOs like Haumea accreted more than 5 million years after that. The dynamical instability probably happened in this time range, 37 to 62 million years. There's actually quite a lot of evidence accumulating that 50 to 60 is the right time frame, but including the moon forming impact. But around this time is when Haumea the impactors, the proto-Haumea and the impactor would start differentiated. They need to start to differentiate so that you can have stripping of whatever's on the outside and yet get down to an icy layer so that after the collision you have ice on the surface. But they can't have gone too far in this because you need Haumea's core to differentiate. And so that puts the timing of when the giant impact happened into this narrow time window if you want to satisfy both of those constraints. The dynamical instability lasts for tens of millions of years. And during this time, the dynamical instability, Haumea was scattered. And then as its core formed and it spun up, then it would have ejected the family member. So it's after it's already in the scattered disk. And then sometime in this time window, it would have actually heated up further, created an ocean. and then that ocean would have frozen, and then by 1.3 billion years, there's no ocean, and but the core heats up and it dehydrates a little bit. Anyway, it's kind of done after that. So we think that Haumea probably had a subsurface ocean for 200 million years and probably underwent this history. And this tells us a lot about when the dynamical instability had to occur. All right, I'm going to move to this other thing that I've worked on, interstellar objects. And I think it's really topical with the discovery the last few weeks of 3I Atlas, third interstellar object, and first light for Vera-Rubin Observatory. We're going to see so many of these objects in the near future. And I really want to emphasize these are probes of exoplutos. And so these are probes of the Kuiper belts, admittedly around other stars, but these are telling us something about our own solar system. So I want to convince you of that. So Haumea, of course, was discovered in 2017 by the Pan-STARRS array, and it was discovered within 5 years of first light of that array. And so that implies something about the statistics of how many objects like Oumuamua are out there. And probably on the order of 10 to the 15-ish objects ejected per star. And that's a surprisingly high number if you're only looking at comets, because we think maybe 10 to the 12 comets were ejected from the solar system. And I'll point out that objects like Borisov and Atlas are probably comets, and they've been discovered at 5 AU. Borisov was discovered by an amateur astronomer. If there were any other objects like that in the last century, they would have been discovered. So comet-like things, we expect a sort of once a century occurrence, and based on how many comets we think were ejected from our solar system. That's about what we see from those comets. Oumuamua is not a comet. It's not one of these objects, and it showed up a lot sooner than you'd expect. And so what is it? And of course, it was observed after perihelion. It approached Earth very closely in October of 2017. And it came in at a pretty small, well, a large, I guess I should say, velocity with respect to the solar system, 26 kilometers a second, but small compared to local standard of rest. The solar system sort of caught up with it. There are many mysteries about Oumuamua based on some of the differences between our expectations, which are based on asteroids and comets, and the observations. So the light curve showed that it was a very strangely shaped object. It's unfortunate that the first thing tried was a cigar shape, because then everybody thought a rendezvous with Rama from that point on. But it was almost certainly a pancake shape with axis ratios of 6 to 6 to 1. It had a non-gravitational acceleration, pushing it always away from the sun and at a strength that is 1 over r squared. And so that is just like what comets do. Comets, because they have sublimation off the sunlit side, is a little rocket effect, and it pushes the comet away from the sun, and the strength of the acceleration varies as 1 over r squared. But the difference between comets and Oumuamua is that this is something like 10 to the minus 4 times the acceleration of gravity, and Oumuamua is 10 to the minus 3 times the acceleration of gravity. It was not making a right angle turn to go visit Earth, but it definitely was a little bit different from comets. And it was observed by Spitzer at 2AU, and there was no detection of CO, CO2, H2O, and kind of tight limits. It could not be made entirely of any of those species. And there was definitely more sensitive to scattered dust, and we didn't see that. And it's also very reddish, about as reddish as many other solar system objects. So we had never seen anything like this, but I want to point out that this is like looking at a platypus and seeing that it has a duck feet, duck bill, and a beaver tail and all this, and saying that this couldn't exist. This couldn't be an animal, because I've never seen an animal like this. All of these features are seen one at a time in different solar system objects, just not at the same numbers in the same object. Well, with Alan Jackson, a postdoc working with me at the time, we hypothesized that it was a slab of ice, and then asked what ice could it be. We rederived the rocket equation to get the acceleration as you sublimate monoliths of ice. And Alan looked up a bunch of ice data, including some from like the 30s, which I found charming, and asked what their sublimation temperatures are, what the latent heat of fusion is, et cetera. And from this, we could make a plot of the acceleration we would predict relative to that is observed. So this is assuming it's like a 1/r² effect, and just comparing the predicted acceleration to the observed one as a function of the albedo of the object and the type of ice that it is. Assuming the albedo is unknown, what ice could it be? And albedo is really important. Everybody who looked at Oumuamua assumed it had an albedo of 0.04, like asteroids. And if it's that dark, it must have been very big. And if it's that big, it's really hard to move. But in fact, if you allow albedo to be a variable, you'll see that the amount of heat you absorb, it goes down as the albedo increases because you're talking about a smaller body, but you also are, the mass is going down a lot faster. So the acceleration kind of scales with the albedo like this, and that's how you generate these curves. And so we can rule out water ice. There's no way a slab of water ice could ever be pushed enough to be consistent with the non-gravitational accelerations. I guess we can't rule out neon, but come on, it's not pure neon. You could rule out CO2 and CO based and methane based on the Spitzer observations. And the one ice that makes sense and gives you an acceleration for two albedos that is consistent with observations is N2 ice. And what was really exciting to us is that one of the albedos you would need for N2 ice to give you the right acceleration is the albedo of N2 ice seen on the surfaces of Pluto and Triton in those ranges there. It's like bang on. So everything about this object is consistent with it being a slab of N2 ice, like you see on the surface of Pluto. These are predictions we made of the distance from the sun, the surface temperature. It never gets very warm because of evaporative cooling. So it's actually inside the orbit of Mercury, but it's still like 50 degrees Kelvin because it's evaporating so quickly. This is like if you've ever gone swimming in the summer in Phoenix and you get out of the pool and it's 110, you're cold and shivering because of evaporative cooling. The mass, though, is dropping very rapidly as it rounds the sun. It probably lost 90% of its mass. And as it lost mass, its axis ratios would have changed. It would have gone from something that maybe was 2-to-1 or 3-to-1 axis ratios, eroding like a bar of soap, to something with a 6-to-1 axis ratio. So we made these predictions and many more, and everything about this object, every observation is consistent with it being an N2 ice slab. And this makes sense because we see N2 ice on the surfaces of bodies like Pluto. And it's not exactly pure, but the CO and the CH4 contents are relatively low, and probably need a little bit of CH4 to tholinize and give it the red color that we see, but it's basically consistent with N2 ice like you see on the surface of Pluto. So where would N2 ice come from? Because although we have an example of N2 ice in the solar system on Pluto and Triton, we don't have many examples of that. Comets don't have a lot of N2 ice. It's probably nitrogen's locked into ammonia, ammoniated salts. But if you think about how a Pluto-like object evolves, you should have stages very early on, including in the first tens of millions of years, where you have oceans in which geochemistry can occur, and all that ammoniated salts and the ammonia potentially could convert to N2. And if the N2 exists in the oceans, it is likely to exsolve during cryovolcanism and outgas onto a surface. So it's reasonable to assume you could have this, and it could happen in the first tens of millions of years. And just looking at the cosmic chemical abundances, a Pluto-like object could potentially have an N2 ice mantle as thick as 35 kilometers thick. And an object like Gongon or Charon with a radius of 600 kilometers, it could be 18 kilometers thick. And it may not be this thick. There's any number of things that prevent the full conversion of nitrogen to N2 and its emplacement on the surface, but we should think about many kilometers of N2 ice. And then this N2 ice, we have to look at what happened in our solar system to imagine how this N2 ice could have been knocked off of planets. And you're probably all familiar with the Nice model, dynamical instability. There definitely was a redistribution of the orbits of the giant planets. Neptune migrated out. This caused the structure of the Kuiper Belt. One thing that I don't know if we fully appreciate is that there were thousands and thousands of Plutos and even more objects the size of Gong during this time, and estimates are 2,000 Plutos and 6,000 Gongs. So there's plenty of opportunities, even though we're stuck with only a few such bodies now. There were thousands of them in the past, and during the dynamical instability that depleted them from the solar system, they also would have caused collisions that would have knocked these fragments off. Looking at the amount of mass that potentially hit each one of those, each Pluto would have been pummeled by a Vesta mass of Kuiper Belt object material at speeds that are typically 3 to 5 kilometers a second. And so this could knock off a large number of fragments. And all of these fragments would be ejected, 20% put into the Oort cloud and 80% into the ejected into the interstellar medium. And we predict something like 0.05 Earth masses of fragments generated and ejected from the system. And most of them would be very small, under 100 meters. We went through a calculation of exactly how much mass would be ejected using the Holsample equations. And there's plenty of room for uncertainty here, but let's just say it's a lot. You're going to knock off many kilometers. We estimate 4 to 11 kilometers of thickness of this N2 ice, and even the water ice from the surfaces. And we predicted the fragments would be mostly N2, but many of them would be water. Most of the debris would be under 100 meters in size. And we came up with about 10 to the 14 ice fragments ejected from our solar system, which is a lot more than comets. And it's not quite enough to explain the likelihood of an Oumuamua, but in subsequent work, we showed that around M stars, the conditions are even better to have more of this ice ejected from solar systems. And so there's actually, it gets you well above the 10 to the 15 that you need. So we think there's a lot of N2 ice fragments, and that they are probing Kuiper Belt objects' surfaces, but from exosystems. Oumuamua specifically probably came from a star system born about 500 million years ago, probably in the next spiral arm, we speculate. But these generally will be a population that will probe Kuiper Belt, exo-Kuiper Belt object surfaces. So getting to my conclusions, you have to use weird tricks to probe the interiors and evolution of Kuiper Belt objects. When did they form? I think probably most of them formed without Illum 26, so more like 5-6 million years, and took tens of millions of years to differentiate. But even small ones could have something like differentiation, where water migrates to the surface, and you probably have differentiation in the insides of larger bodies, but maybe not the rock ice crusts. Those are hard to get rid of. I think that if Oumuamua is an example of an object that you know, is N2 ice from the surface of a body, then that must be a very common thing. And we probably should think about many, kilometers of N2 ice existing on each of the thousands of Plutos in our solar system. And as we probe more interstellar objects, we'll be able to test that. And yeah, and finally, I think that the evolution of Haumea and Pluto is showing that the dynamical instability probably happened right around 50, 60 million years ago. So weird tricks to understand the interiors of KBOs. Thank you so much for your attention.
Thank you. We have time for questions. And a reminder to those online that you can raise your hand or send your question via chat. So I'll ask a question while people are coming to the mic. Would you predict nitrogen ice slabs within the solar system, sort of comet, like hanging out in the Kuiper Belt or in the Oort cloud? If you do, where are they?
Great question. Yes, although over 4.5 billion years, they tend to be eroded by galactic cosmic rays. So This is one of the reasons that we think Oumuamua itself is not billions of years old, maybe 500 million years old. But there is an object, comet 2016 R2, one of these blue comets that is very N2 rich. Its chemistry is very different. Vivet et al. 2018 identified it as a slab of a differentiated Pluto. There's probably a few more. So yes, definitely, I think we have a few percent of comets would fit this.
Hi, Steve. Elliot Young, Southwest Research. Here's a question which probably won't withstand sunlight. Is there anything you can think of that can increase porosity, like a close encounter or a phase change of an ice, or is porosity always decrease?
Oh, that's an interesting question. Yeah, obviously, if you disassemble an object and reassemble it as a rubble pile, you'll have macroporosity. If you crack rock through thermal expansion, for example, you can definitely introduce some microporosity, which wouldn't show up in a mass radius relation, but there are ways, but generally, yeah, it collapses.
Brian Holler, Space Telescope Science Institute. For the Haumea family formation theory, did you look into whether or not that can replicate the orbital positions of Namaka and Hiaka? Does it predict additional satellites, additional rings, anything like that?
Oh, those are great questions, and I wish we could have done that. What we can do is predict the existence of about 3% of a Haumea mass in a ring of material that is basically right outside. It's at the tip of its long axis, and then we speculate after that it should coalesce into moonlets, that these could viscously spread through dynamical friction and then migrate out. It's really interesting that Haumea has this 3-to-1 resonance of the outer edge of its, or that's where the ring is. It's just like Chiriclo and I guess Quaoar. There's a lot of dynamics after this that we just don't model, but yeah, it'd be really great to see that modeling.